Thanks, Warren. And I'd like to recognize my co-author, Bailey Engel, who's contributed a lot to this presentation. Why don't you stand up, Bailey? Bailey's a new scientist at the U.S. Meat Animal Research Center and is really passionate about beef cattle breeding. And I'd encourage any of you who don't know her to introduce yourselves to her. Okay, so I'm going to cover this presentation in 3 parts. And so first, we're going to start with rewarding high quality data. Then we're going to talk about some other improvements that could be made in the genetic evaluation system to eliminate some noise. And we're going to take a pretty high level view of those problems in those 2 sections. And then I'm going to wrap up with a section in which we get into the weeds and really drill down into some of the technical basis for these proposed improvements. So I'm going to start with rewarding high quality data. Some breeders report high quality data for use in genetic evaluation, or higher quality data for use in genetic evaluation than others do. And our current evaluations don't reward high quality data with higher reported accuracies, although the EPDs that they produce are in fact more accurate. But nonetheless, it should be possible to report higher accuracies for higher quality data. And that's the objective of this presentation. So what do we mean by high quality data? Its measurements are made accurately using appropriate instrumentation. They're made under appropriate and uniform conditions. The pedigrees are recorded accurately and verified by Genomics. Contemporary groups are formed correctly. All optional information that is requested is provided. And the information is recorded with the intent of obtaining accurate evaluations instead of with the intent of obtaining favorable evaluations. So the objective is that genetic evaluations should consider data quality in 2 distinct but related ways. They should increase the true accuracy and effectiveness of selection of animals whose evaluations are based on high quality data. And that accuracy that's reported along with EPDs should be more reflective of true accuracy than it currently is. And they should put more emphasis on high quality data and de-emphasize the low quality data. And the effect of that is to increase the overall accuracy of the genetic evaluation. So fortunately, the same improvement to the evaluation can accomplish both of those things. So we're going to talk about reducing noise in data and what we can do with evaluations to do that, and to make sure that everybody is familiar with what I mean by noise. You're all familiar that with an AM radio, you get a lot of noise and it's a little bit hard to detect the signal. But if you have a digital recording, the signal is very clear because there's little noise. And so in genetic evaluation, the signal is the true breeding value. The signal is the true breeding value, and the noise can come in a lot of different forms. It can be measurement error, it can be pedigree error, it can be environmental variation. And one that I just heard of the other day is that we could have a feed efficiency test and we pull some bulls out to collect semen on them during the middle of the feed efficiency test. That definitely qualifies as noise. We can't eliminate noise, but there are things that breeders, breed associations, and genetic evaluation providers can do to reduce the noise and its impact and to increase the rate of genetic progress. And a couple characteristics of noise: our signal to noise ratio is going to determine the rate of genetic improvement, and less noise is going to result in higher heritability and greater accuracy. So several years ago, Matt Spangler presented an approach to improve data quality in genetic evaluations. And this was a very specific approach. It was based on artificial intelligence, and it dealt with a problem in birth weight where the idea is that a lot of what's reported as birth weights is not actual weights. And so Matt, working with Bruce Golden and others, developed a machine learning algorithm that would classify records into those that are most likely to be true weights and those that are most likely to be something else. And that's a really good way to improve data quality. But it's a very specific way. It deals with a particular trait and a particular problem. So what I want to talk about is a more general way to improve data quality. And it's based on estimating the amount of noise that's in the data provided by each ranch, and then adjusting the genetic evaluation algorithm so that it takes into account the amount of noise that's estimated by each ranch. And I'm going to get more into the details of the implementation of that in the last section of the presentation. But I just want to point out here, this is a general approach that could be applied to all traits and is not really specific to a particular cause of high or low data quality. And it's not an alternative to what Matt proposed, but they could actually be superimposed on one another and have benefits in doing that. And another aspect of this approach is that it could allow us to estimate a ranch-specific heritability that breeders could then use to benchmark the quality of the data that they submit relative to that submitted by their peers. So I'm going to get a little, change gears a little bit and talk about other things that we could do to reduce the amount of noise that affects our genetic evaluations. And a lot of that has to do with how we handle contemporary groups in the evaluation. And the way we handle contemporary groups in beef cattle evaluation, I think in some of the other species as well, is basically the same way that we did it about 50 years ago, when the computers at the time would have filled an entire room and had orders of magnitude less computing power than most of the wristwatches that we wear today. And the way that that's set up made a lot of sense when computers were so limited, but it doesn't really make sense today, and we're really not capturing all the information that's available to us by using the same model that we used 50 years ago. And so we're going to talk about how we might change the way we handle contemporary groups. And in doing that, we need to also think about other effects that could be included in our model that are not genetic effects, but things that would allow us to take noise out of the genetic evaluation. And together, I think that these things should provide a quantum leap in genetic evaluation. So the primary thing that I think we need to consider in terms of fitting contemporary groups is that currently contemporary groups in beef cattle evaluation are fit as what we call fixed effects. And what that means is that each contemporary group basically has its own average independent of other contemporary groups. And we're proposing that they should be fit instead as random effects. And in that case, contemporary groups from the same ranch share information such that their averages are more similar than they would be if fit as fixed effects. And changing from fixed effects to random effects for contemporary groups is going to have relatively little impact on large contemporary groups, but it has a big impact on small contemporary groups, and it allows us to extract more information from those smaller contemporary groups. So a lot of animal breeders would say that the contemporary groups naturally should be fit as random effects, but historically there have been a lot of practical reasons why we have not fit contemporary groups as random effects in beef cattle breeding and I'd say dairy cattle breeding as well. But the random contemporary group effects need an overall mean for the contemporary groups to be centered around to be applicable in large national field data evaluations. And so that's what we're proposing to do. And that involves requiring what I'm going to call a ranch ID effect. And in general, a ranch ID could be as simple as the breed association member ID of the owner of the cattle at the time that the measurements are made. But there are a few edge cases in which it would be different, and that could involve cases where, for example, we have a family operation and the cattle are registered to individual family members, but they're all commingled on the ranch. And so in that case, we'd need to merge several member IDs into one ranch ID. There could be ranches also that, or breeders that have ranches that are in different environments, and we might want to separate that out and have a separate ranch ID for each of the ranches owned by the same member of the association. One of the things that really contributes to small contemporary group sizes is that our BIF guidelines specify that calves of different sexes should be split into separate contemporary groups. But at birth and weaning time, the calves typically have all been run together as a group. And we lose a lot of information by breaking up that information into independent contemporary groups. And so we really should think about all those cattle that were raised together should remain contemporaries. And then we handle sex as an independent cross-classified effect. And we can do a much better job of estimating sex differences if we're doing that across a lot more calves than what are within one pasture of calves that were weighed or managed together. Another issue that a lot of us have with the current definitions of contemporary groups is that contemporary groups can only become smaller over time. We can't ever take two different groups earlier in life and combine them into a larger contemporary group for subsequent measurements, according to the BIF guidelines as they are currently. And so this is the other primary contributor to contemporary groups that are smaller than they really need to be. And consequently, they contribute less information than they could. And so we want to propose a way in which contemporary groups are based on the way that cattle were managed together as a group in the time period immediately preceding the measurement, and then we adjust that data for the effects of contemporary groupings earlier in the animal's lives. And we think that's practical to do. Some of the things that we would like to do to reduce noise in the evaluation might be things that a few breeders would participate in, but a lot wouldn't participate in. And so we're proposing that these things should be optional, and the model should be able to account for these factors either being included or not. An example of that would be that when we gather a group of cattle and weigh them, and if it's more than just a couple of cattle, those cattle are going to shrink during the time that we have them gathered. And so the later or the more time that's elapsed between when they're gathered and when they're weighed, the more they're expected to shrink. And so if we had the time that each of those weights was taken together with the weight, then we could adjust that data for the shrinkage, and that's eliminating noise. Now, not all breeders are going to do that, but the ones who really care about data quality and have electronic scales and good data handling capabilities can probably do that without much difficulty. So it's something that can be optional, but then those who provide it should be rewarded with higher accuracies. And those higher accuracies are going to give those breeders the opportunity to have greater selection response, and then also their herd-wide heritabilities will also be higher as a consequence of that. So in order to make all these changes, things have to happen at a lot of different levels. There are changes that ought to be made to the BIF guidelines. Breeders need to correctly specify contemporary groups, and to get the highest accuracies, they're going to need to participate in these things, provide information that's optional. Breed associations need to provide the flexibility for breeders to provide additional information that's not captured now, and the opportunity to handle data that's optional and use what's there and don't worry about what's not there. And then the genetic evaluation service providers are going to have to make some changes to the genetic evaluation model and to be able to fit some effects optionally and a few other things like that. So I'm going to switch gears at this point and provide more details on what the implementation of this would look like, some additional things that we ought to be thinking about including in our genetic evaluation models. I hope everybody's been able to take at least something home that you hadn't thought about before up to this point. I think there's still something for everybody to take home, but I'm going to, from this point on, become unapologetic about using more technical language to communicate to the people who really need to implement this. And if that's not for you, feel free to get up and do something that's more productive for you. I hope you'll stay and get something out of it, but you know, just don't be offended if we go over your head on one or two things. So if there's anybody that has a question at this point that wants to leave, I'm happy to answer questions. All right, well, that's great. We'll just keep going. How are we doing on time, Warren? So the real elephant in the room, and I'm going to say this is the only slide that has mathematical formulas on it. It's the most technical thing we're going to go through. But the elephant in the room is, how do we actually implement rewarding high quality data with greater accuracy? And the short answer for that is that we want to estimate the residual variance for each ranch, and then we want to make the genetic evaluation conditional on ranch specific residual variance. Okay. And so for those who need to implement it, they know what that means. And then the other part of the big elephant in the room is, is it actually feasible to do the computations required to do that? And so the formula that's here explains how we would do that. And so for those who know and care, what we basically need to do is to condition on all of the variance components, except for the the residual variance for one trait at a time. And then within that trait, we're going to estimate residual variance just like we would on an overall basis for the entire evaluation. But what that basically is we're going to take the vector of observations, that's the y prime, and we're going to multiply each element of that by the corresponding residual. We're going to sum that up over the animals at that ranch, and we're going to divide it by the number of degrees of freedom in that data. And that's a pretty simple computation. It just needs to be what we do to estimate overall residual variance is we sum that over the entire evaluation. And now we just need to sum it by ranch and divide by a smaller number. So it's not a lot more computation. It obviously requires software to implement it, and that doesn't come free. But then the other part that's potential cost for implementation is that the evaluation has to then use those ranch-specific residual variances instead of operating on one residual variance per trait across the entire evaluation. And so if that's not already available in the software, adding that is something that has to be done. And then there's a little bit more for multiple trait evaluations, which essentially all of our evaluations are, but that's a pretty trivial thing to implement. And what I've described is what we would do for the kind of traditional approach to computing genetic evaluations. Some of our evaluations are based on a Monte Carlo approach implemented through Bolt. And that's going to be a little bit different, but probably not harder and maybe easier than what I just described. So that's the end of the real mathematical part of it. There are a few details about fitting contemporary groups as random effects, and that requires a ranch ID that I already defined because we need to estimate a mean for each ranch, and that mean will change over years, and so we probably need to fit a within ranch regression in addition to the mean for each ranch. We have an advantage in that we have contemporary group of effects for multiple traits, and if multiple traits are collected at the same time, we have the opportunity then to estimate the correlation between those contemporary group effects, and that actually allows us to do a better job of estimating those contemporary group effects. And so that's one of the advantages of moving from contemporary groups as fixed effects to contemporary groups as random effects. And then one of the things that changes when we move to random contemporary group effects is that the definition of what is phenotypic variance that goes into heritability becomes a little bit ambiguous. Do you add in the phenotypic variance that's due to a random contemporary group or not? And our consensus is that you don't add it in. And so it's not really all that different, but it is a question that arises. Another thing that becomes a little bit trickier with random contemporary groups is what do we do with management codes? So most breed associations and the BIF guidelines stipulate that breeders should be able to submit management codes along with their data. And I think that the original intent of management codes was that they would specify cattle that were managed differently, as I've got listed here, cattle that were on range versus high quality pasture versus developed in a feedlot or fitted for show. And, you know, in some cases, people would manage their first calf heifers separately from mature cows, and that could be a different management code. In my experience, what management code has been used for more routinely is that for breeders who have multiple groups of animals that maybe were managed on average about the same, but just in separate groups, but they're in large groups, breeders would assign different management codes to the different groups of animals so that our contemporary groups took that grouping into account. And those are really two different ways of using this same field that has the same name. And what's important about that is that that first group needs to be fit as fixed effects. And the second group, in other words, animals that were managed had the same expectation for management effect, but were managed in separate groups, then that should be part of the random contemporary group definition. And so somehow or other, we're going to need to probably take this term management group and specify, or management code, specify what that means and come up with another terminology. And it probably means another field within the data request from the breeder to the association, or from the association to the breeder, so that we separate out those two different things so that each of them gets handled appropriately. Okay, I've long had an issue with how the BIF guidelines define contemporary groups. And they basically say if they're managed similarly, they can be contemporaries. My experience before working at US Mark was working for large breeders who had a lot of different groups of cattle that were contemporary. And I never sent animals that were managed in different groups in as contemporaries with one another. But I do understand that for small breeders, there may be cases where groups of cattle are managed differently, and if we break them up into small contemporary groups, there's not a lot of information left in a bunch of contemporary groups that are 5 animals or less, for example. But with a move to random contemporary groups, this situation changes. And with random contemporary groups, animals that are managed separately should be in separate contemporary groups. And that is going to benefit these small breeders who have small contemporary groups. As long as one of those small contemporary groups isn't the cattle that are being fed cooked barley in the show barn and the others are out on pasture. That's a fixed effect, and that needs to be accounted for through the management group. But so our assessment is that going forward, the definition of a contemporary group should be those animals that were managed in the same group. And it's not breaking them by sex. It's not breaking them by other things that might be different that are in the current guidelines. It's just whatever animals are managed together in the same group. That's the random contemporary group that we want to fit as a random effect. So, I mentioned some of these, the guidelines currently allow animals that are managed separately to be submitted as the same contemporary group. And what's the effect of doing that? Well, if you do that, the reported accuracy of those calves is going to be higher if you submit them as all being contemporaries than if you split them into 2 different contemporary group effects. That's just a mathematical fact. But if the mean effects of those 2 groups is much different, you could have a reduction in the true accuracy of the evaluations of those calves by combining them into the same contemporary group. You'd have a better prediction of true accuracy if you submitted them as separate contemporary groups, so that the contemporary effects that those records are adjusted for are more accurate. And so it's a bit of a conundrum, and it illustrates the difference between what reported accuracy is and what true accuracy is. True accuracy is the correlation between EPD and breeding and true breeding value. So, so combining those contemporary groups when they're not really contemporary can cause less response to selection and reducing the true accuracy. So how do we handle this situation I mentioned earlier, that we'd like to be able to wean calves out of multiple pastures? Each pasture has its own contemporary group, but then at yearling, what do we typically do with them? We put all the bulls together in one group, and we put all the heifers together in another group. So I've always believed that for post-weaning gain, for example, all of those bulls should be a contemporary group. All the heifers should be a contemporary group. And what we're proposing is that we think there's a way statistically to adjust each of those bull records for the contemporary group effects that they had prior to being combined, and to adjust all those heifers for the contemporary group effects that they had prior to being combined. And so I think it's a solvable problem, and we need to do a bit of work on it. But I think that that's going to be important going forward. I think it has minimal computational cost. When we think about collecting data on cows as they go through their lifetime, cows often get resorted from year to year, if not multiple times within a year. And so an approach to be able to deal with this in the cow herd, I think, is especially important. And we've heard a lot in this conference about high throughput phenomics, collecting information on animals more or less continuously in real time. And, you know, we're not going to be able to, in terms of producing contemporary groups for that kind of data, we're not going to be able to make contemporary groups continuously smaller and deal with that data effectively. So it's an issue we're really going to have to need to be able to deal with going forward. Another thing that we've started fitting in our models at US Mark, and that I think we should be fitting in genetic evaluation models, is regression on birth date. Even on weaning weight, we can apply a 205-day adjustment, but in general, a 205-day adjustment favors young calves over older calves. And if we've got a linear regression, that helps to take that noise out of the evaluation. And if we do that, I think we need to worry less about putting age ranges on what animals can be considered contemporaries. I think that's less of an issue than it used to be, because breeding seasons tend to be shorter than they used to be. So I assume probably there's less cattle that get split into small contemporary groups at the end of a breeding season than used to be the case. But you know, that's a real loss of information that we really shouldn't be imposing on ourselves. And you know, we have those age ranges that some breed associations and apply as birth weight slices, and I think we lose a lot of information through that. And that if we would just regress on birth date, then we ought to be able to take the cattle that were managed together at the time that the cows calved, and not have to be breaking contemporary groups arbitrarily like that based on birth date. That does require capturing from breeders how the cows were grouped at the time they calved, and I don't know that that's routinely done currently. But I think it'd be a real improvement. There's another effect that I think we need to take a hard look at, and it's a pretty tricky one, but it's pretty typical to start a breeding season out doing AI. And then at some point, we stopped doing AI and we put cleanup bulls in. And we generally treat all of those as contemporaries. And there's various things that have changed along that time, especially if we're not fitting a regression on birth weight. We've got temporal changes that are different between those. And those temporal changes could get confounded with our estimates of genetic differences between the AI bulls and the cleanup bulls. Even if we do fit the regression, there's still a possibility of having confounding there. This is something we've been discussing recently. I think it's a really sticky problem. I don't know what the answer to it is. I fear that if we estimate that effect, it's going to be partly genetic and it's going to be partly non-genetic. And we need to really think about how we can partition it. One of the things that makes it even stickier than what I've described so far is that we do get a set of calves. There's a period of time when we're having both AI calves and natural service calves born at the same time, right? During that transition from AI to natural service. And our statistical model could say, oh, that's great. That gives us a great way to compare AI calves to natural calves. And they're all contemporary, so everything's wonderful. But the problem is that when that's happening, the AI calves that we're getting are the long gestation ones, and the natural service calves that we're getting are the short gestation ones. And so that could really introduce a bias into that estimate. But I still fear that not trying to fit that effect also has unintended consequences. And so I don't know what the answer to this one is, but I think it's something that deserves more attention than it's been given. And I think there are similar issues with ET calves versus AI calves. I know some people would put the ET calves in a different contemporary group. I would rather, if they're managed together, they're in the same contemporary group, but we fit an effect to account for them. I think there's less danger of bias in ETs versus AIs, which typically are probably being produced at the same time. I mentioned earlier, we could do regression on time of measurement. Okay. That could also be done without timestamps. If you just have the order in which the calves come across the scale, you could compute a regression on that just as well. There's another issue. I'm just going to skip this one because it takes a little bit longer to talk about. So there are a number of other things that we could add to the evaluation model, but this is a list of the fixed effects that I think could go into the evaluation model. That'd be ranch ID. We should have a management code nested within ranch ID. Sex of calf is going to be an effect that's cross-classified with contemporary group. Age of dam effect, same thing, cross-classified with contemporary group. ET versus AI versus naturals, going to be nested within ranch ID. Nested within ranch ID, but cross-classified with contemporary groups. Regressions on previous contemporary groups within ranch ID, regressions on birth date and time of weight within ranch ID. And then that leaves us for random effects. The non-genetic ones are contemporary group nested within ranch ID. And then potentially we could have random effects per ranch that are nested within the overall cross-classified fixed effects for things like sex of calf, ET versus AI versus natural, age of dam. We'd need to evaluate whether those are computationally feasible in the evaluation or not. But if they are, they probably give us a bit more information. And so I think there's a lot we can do to make genetic evaluation more accurate by reducing the noise. So we focus a lot on the genetic effects in the evaluation, but we haven't done much about reducing the noise or accounting for it. I think there's a lot of opportunity there. Both large and small breeders will benefit. It has more opportunity to benefit small breeders. But the other thing is who will really benefit is the people who go to the effort to submit high quality data. And my hypothesis is that the folks who are in this room are going to be at the upper end of the quality distribution.